All right. For number one, I would start by using one of the odd-even identities. Specifically, I would use 4. And then I'm going to use reciprocal identity 4. And then I'll just reduce to get -1. Angela? No, we'll talk more about what the expectation is when it gets a little bit closer. Probably not. The next one, I'm going to start by using P2. To replace cosecant squared with 1 plus cotangent squared, I'll distribute my negative. Those guys cancel, and I'm left with -1. Three, what I did is I used Q2 on the cotangent squared and then Q1 on the tangent squared. So I'd have cosecant squared x over secant squared x all over cosecant squared x plus secant squared x over cosecant squared x all over secant squared x. I'll reduce my fractions here. That leaves me with 1 over secant squared plus 1 over cosecant squared. And then I'm going to use R1 and R2 respectively to rewrite secant squared, or 1 over secant squared is cosine squared, and 1 over cosecant squared is sine squared, which, according to P1, is 1. So that's it. That's how you did them. 3 minutes. Would have been plenty. So, was this the only route you could have used it to get to the correct answers? No, there's a lot more circuitous routes to get there, but these were the quickest ways, I think, to have ended up there. All right, next up, let's talk about the homework from last night. So if you guys can take out your 15 to 30, we'll take some questions from that. So probably 20 minutes or so of questions, and that'll probably be good. So just let me know whatever it is you guys want to talk about here from this set. I'd be happy to kind of go through and do some of these. Annika? 24. Okay. So first things first, I would take sine inverse of both sides. And then I'm going to go to my unit circle and find the places where the y-coordinate is -1. That happens exactly once at 3 pi over 2. So that's my answer for A. My answer for B, well, it asks for x is on the interval from -infinity to +infinity. So basically, I just need everything that's coterminal to 3 pi over 2. So I'll just do that by adding all the multiples of 2 pi to it. C, the interval is from negative 2 pi to positive 2 pi. So clearly my answer for part A is in there because that's from 0 to 2 pi, right? Now there's also another answer on the interval from negative 2 pi to 0. How can I find that answer? I'll just subtract 2 pi from this. That'll give me a coterminal answer that's smaller than it. So when I do that, I get negative pi over 2. And if I subtracted 2 pi again, obviously I'd have something too small, right? Whatever would be left would be less than negative 2 pi. So I'll stop there. Those are my answers. And then D is negative pi to 4 pi. Well, I know that my answer for part A is one of my answers because that's 0 to 2 pi is certainly inside of negative pi to 4 pi. And my other answer for part C is here because that answer is from negative pi to 0. Everybody agree with that? And then I just now have to worry about the things from 2 pi to 4 pi. How would I find any answers there? Just find something coterminal to this, right? So I'll do that by adding 2 pi. When I add 2 pi to that, I get 7 pi over 2. And that would be the only answer in that interval. So those are my 3 answers for part B. Is that okay, Erika? Sure. Well, you're always adding 2 pi. It's just in some of the situations, you could combine some of those answers and just do, like you have 2 answers that are like something plus 2 pi and something else plus 2 pi. But if the distance between those is only pi units, you can combine those 2 answers and just write one answer plus pi. So, for example, like you had an answer that was here and here, and the distance here is pi, and the distance there is pi. I'm just going to say that answer was alpha and that answer is beta. Instead of writing alpha plus 2 pi k and beta plus 2 pi k, you could just write alpha plus pi k, because if I add pi to alpha, I'm at beta, right? So it's going to cover, like those 2 solutions are equivalent to this one. No, it's just not like the simplest way you could write it. It'd be like leaving your answer as 4 over 2. Right? Like, it's not wrong to leave it as 4 over 2, but like, we don't really write it as 4 over 2. You know what I mean? Okay. Does that help? Because I did that frequently on there, right? You saw lots of them that had pi's there instead of 2 pi's. And that's all that was going on there, is just simplifying, writing fewer answers by combining 2 of the solutions into one, basically, which is what I demonstrated here. Does that make sense? Frequently when you're dealing with tangents, this happens. I think almost all of the tangent ones you can do this too. Okay. Who else has some questions here from this set? Colette. 20? Sure. So we have tan squared of x is equal to 1/3. So first thing we do is square root both sides. And then to solve this, I'd have to split it into 2 separate equations and take the tan inverse. okay with that so far, Colette? Now what I'm going to do is go to my unit circle and look for the places where tangent is equal to 1 over the square root of 3, positive or negative. I remember on the unit circle, tangent is equal to y over x. So I'm looking for an x coordinate on my unit circle that involves a square root of 3 in it. So if I look, that would be something like pi over 6. So that would be y over x. And when I simplify that, I would end up with 1 over root 3. Okay with that? So I would have for positive, or tangent of positive 1 over root 3, I'd have pi over 6, as well as 7 pi over 6. And for the negative, I'd have 5 pi over 6 and 11 pi over 6. So that's my answer for A. Are you good with how I found those values, Colette? Okay. For part B, now notice that I could write this as like 5 pi over 6 plus 2 pi k, and then 11 pi over 6 plus 2 pi k. But really, I can take these two solutions. Morning. Just FYI, you missed the homework quiz that you'll have to find a time to make up at some point.
I have to talk for the parents.
Yeah, that's no, it's at your convenience. Yeah, not a big deal. Sure. So notice that between 5 pi over 6 and 11 pi over 6, that's exactly 6 over 6 pi apart, or 1 pi difference. You guys see that? 11 pi minus 5 pi is 6 pi, so 6 pi over 6, they're a difference apart. So I can combine these into one answer and just write it that way. Similarly, we can do the same thing with the other two answers. Which again, those are also pi units apart. So I can do the same thing and combine those into one solution as well. Does everybody kind of see what I did there and how I got to one solution and just went from 2 pi down to 1 pi? C, we want from negative 2 pi to positive 2 pi. So clearly all our answers from before in part A are going to be answers still here, right? So these are the answers from 0 to 2 pi. What we need also are the answers from negative 2 pi to 0. Everybody okay with that idea? So how would I find those answers? I just need a negative angle that's coterminal to each of these. So I would get that just by subtracting 2 pi from each of these. So that would be negative 11 pi over 6, negative 7 pi over 6, negative 5 pi over 6, and then negative pi over 6. And then for part D, we wanted negative pi to 4 pi. So definitely my answers for part A should all be here, because 0 to 2 pi is contained inside this interval. And then if I want, say, the stuff from negative pi to 0, well, let's look at my answers for part C, because some of these are too small, right? Specifically, this guy and this guy are both less than negative pi. So I wouldn't want to include those, but I do want those ones. And then I have to worry about the stuff from 2 pi to 4 pi. How am I going to find that? I'm just going to take my answers inside the unit circle and find an angle that's coterminal to these, that's bigger than them. Specifically, I just need to add 2 pi to each of those. So when I do that, I get 13 pi over 6, 17 pi over 6, 19 pi over 6, and 23 pi over 6. So that would be the solution set then for part B. Colette, are you happy with that? Do you see what I did there? And hopefully we're seeing how I'm using my previous answers to like build the next answer out. Okay. You didn't have all 4 on the unit circle. Did you forget the plus or minus? Yeah, that would do it. Ben? 16? Sure. So cosine of x is 1/2. So, oh, thank you, negative 1/2. So we'll do the cosine inverse to both sides. Then I'm going to go to the unit circle and look for places where the x-coordinate is negative 1/2. That happens at 2 pi over 3, and also again at 4 pi over 3. So that's my answer for part A. For part B, all I'm going to do is add 2 pi k to each of these. Notice that the distance between these is not pi, right? If I were to graph these things, one is here and one is here. So they're not symmetric. So I can't combine those two infinite answers. I would need them separate. C is from negative 2 pi to positive 2 pi. So my answers for part A should still be here. But I also need the stuff between negative 2 pi and 0. I can get that just by subtracting 2 pi from each of these. So that would be negative 4 pi over 3 and then negative 2 pi over 3. And then for part D, we want from negative pi to 4 pi. So my answers for part A definitely need to be there. Some of my answers from part C need to be there. Negative 4 pi over 3 is too small. That's less than negative pi. But that one is okay. That one is bigger than negative pi, so that one should be there. And then I just need the things that are between 2 pi and 4 pi. Well, I can find those by just finding angles coterminal to my answers from part A that are bigger. So I can just add 2 pi to each of those. And that should be my solution set for D. Okay with that, Ben? Good. Of course. Anybody else here? Annika? 22? Okay. So we'll take tan inverse of both sides. Remember, on the unit circle, tangent is y over x. So that is true exactly when y is equal to 0. Right? A fraction is equal to 0 only when its numerator is 0. Everybody's okay with that idea? Okay. So that happens at specifically 2 locations, at 0 and pi. Notice that those 2 values are pi units apart. So this is one that I could write as with a pi k instead of a 2 pi k. And notice that 0 plus anything is itself, so I'll just write it as pi k instead of 0 plus pi k. It's not wrong to write the 0 plus, but you can simplify. Of course. Anik, you okay with that? All right. On to part C. So C, we have to be very careful here. Remember in part A, we're going from 0 to 2 pi with the parenthesis. Here we're going from negative 2 pi to positive 2 pi, both with brackets. So here my answers are negative 2 pi, 0, and positive 2 pi. Why wasn't, or I'm sorry, I got more than that. Negative pi, 0, pi, and 2 pi, excuse me. Why wasn't, say, 2 pi an answer up here in part A? Because I had a parenthesis on that interval, so I know that 2 pi isn't included in that interval. Here it has a bracket, so I know 2 pi is included. This one is a very sneaky one where you really had to pay attention to whether these were open or closed intervals here at the ends. You have to that? It given to me in the directions, right? The intervals that we're solving over are in the directions. So that's why I've been citing those over and over again. But you had to be careful on this one in particular. In all the examples to this point, it hasn't mattered. But here, the intervals definitely matter because our answers are potentially at these endpoints. So on this one, we're going to go negative pi, 0 pi, 2 pi, 3 pi, and then not 4 pi because the parenthesis there. Is that okay, Annika? Yeah, so this one was sneaky because of the endpoints, right? It's like, why is 2 pi included here but not there? Why, But if you looked at the intervals carefully, it's like, oh, that's exactly why it's in that one but not the next one. Probably have time for one more. Does anybody have one that they want to talk about? Well, I want to at least point out something here. If you guys looked at, say, 26, we have sine x is equal to cosine x. Anybody figure out the trick to deal with this? Seems like we can't deal with this, right? Try again. Here's the trick. If I divide both sides by cosine, the left-hand side becomes tangent, and the right-hand side is then 1. So this then would be the same as number 17. In the homework, if you ever catch a problem that like, oh, this turns out that it's exactly the same thing as something I've already done, you need to redo it. You can just like cite that it's the same problem as something else and just stop. If you've already done that other problem, it's fine. Is everybody okay with that trick? And that's a common trick. We'll use that frequently when we're solving to like, if you have a sine and a cosine and you can't like figure out a way to combine them together somehow, you can do this, divide both sides and turn it into a tangent. Then? No, they're coming back here in the third section. And they're coming, and then I would say they're even potentially coming back in the next solving section. So we have one more solving topic after today that I still need to talk about that will potentially involve some identities as well. Okay. So I would say this is part 2 of solving. So let's say that we're solving the equation sine of 2x equals 1/2 on the interval from 0 to 2 pi. Morning. What's been different about this problem than any of the previous ones we've looked at so far? We have this coefficient on the x. And at first glance, maybe this doesn't seem like it's going to be a big deal. So if we approach this the same way we'd have in the previous problems, we'll take the sine inverse of both sides. And then we'll go to the unit circle and retrieve the places where sine is 1/2. So we're looking for where the y coordinate is 1/2. That happens at pi over 6 and at 5 pi over 6. And then you probably just think, okay, we'll just multiply both sides by 1/2 then. And I can say x is pi over 12 and 5 pi over 12, right? Seems like there's nothing wrong with that. And those indeed are answers to this, but they're not all the answers that we need. Let's explain why we're missing some answers by asking a similar question. We'll come back to this one and fill in what the missing answers are. But first, let's answer this question. So solving the same equation, sine of 2x equals 1/2, but this time we're solving it over the whole real line. We want all of the answers. So just like before, we'll take the sine inverse of both sides. And then we'll go to the unit circle and retrieve the values where sine is equal to 1/2. So we get our pi over 6. But since we're solving this over the whole real line, we also get the plus 2 pi k. And we also get 5 pi over 6 plus 2 pi k. Everybody's okay with where the 2 pi k is coming from? Okay. Now, when I multiply both sides by 1/2, we get that x is equal to pi over 12 plus pi k, and 5 pi over 12 plus pi k. Everybody's okay with how I've gotten to here? So let's return to that very first example. We had these two solutions. This is when k is equal to 0, right? If I plugged 0 into my answers before, the infinite solution, we would get those two specifically. If I let k equal 1, I'd have pi plus pi over 12 and pi plus 5 pi over 12, right? So that would give me 13 pi over 12 and 17 pi over 12. Are those between 0 and 2 pi? Yeah, they are, aren't they? Those were our missing solutions. If I did it again, if I let k equal 2, I'd get things that are too big, right? Now we'd be adding 2 pi, and certainly adding 2 pi to something that's positive is going to be bigger than our interval 0 to 2 pi. So everybody's okay with how I found those other two mystery solutions? Is I really just used the infinite answer and then just built out as much as I needed. Here's my question. Why am I getting 4 answers here all of a sudden when I normally was getting 2? Can somebody give me a geometric explanation for that? Okay. So remember back when we graphed these trig functions? We talked about this as the general form. So here's like our coefficient for x, right? What transformation was this in charge of? Yeah, this was the horizontal stretches and shrinks. So what's happening is, if this is our graph for, say, like sine of x, and say the green is the graph for sine of 2x, oops, I wrote that wrong. That's supposed to be this. This graph is going to look like that. So if this is the line for y equals 1/2, notice the red has 2 solutions, right? There's 2 places that intersect that blue line. And the green has 4 solutions, right? Everybody can kind of see that graphically. So because that coefficient is causing a horizontal stretch or shrink, you're going to either get more solutions than you anticipated or less solutions than you anticipated if there is no transformation in that regard. Does that make sense to you guys? And it's really predictable on how many solutions you're getting. So if this coefficient is 2, we're expecting twice the amount of solutions. If that coefficient was 3, we'd expect 3 times. If the coefficient was 1/2, we'd expect half as many. So it's really, it's nicely predictable on how many you should be looking for, which is nice, right? Let's do another example here, where we don't have to go jump back and forth. So let's say we wanted to solve cosine squared of 3x equals 1/2 over the interval from 0 to 2 pi. So my recommendation here is that we find the infinite solution first, and then we use that to generate all the solutions that we need by choosing values for k appropriately. So I'm going to start by the same way we have and square root both sides. When I rationalize my denominator, I get plus or minus root 2 over 2. Because of the plus or minus, we'll break this into 2 solutions to solve. So I get 3x is equal to the cosine inverse of negative root 2 over 2, and 3x is equal to the cosine inverse of positive root 2 over 2. Are we so far so good? Okay. I'm going to go to the unit circle now and retrieve the places where cosine has the value of negative root 2 over 2. That happens specifically at 3 pi over 4. But because I'm using the infinite solution, I'm going to write the plus 2 pi k. And it also happens at 5 pi over 4. And again, I'll write that plus 2 pi k. And similarly over here, except I'm looking for locations where cosine is positive root 2 over 2. So that's going to be pi over 4 plus 2 pi k. And then again at 7 pi over 4 plus 2 pi k. Now I'm going to get the x by itself. So I'm going to multiply both sides of these equations by 1/3. So I'm going to get x is equal to 3 pi over 12 plus 2 pi k over 3. Now, I recognize that 3 pi over 12 can be reduced, and I will reduce it in my final answer, but it makes the adding fractions part that I'm going to have to be doing here a little bit easier if I can just like stick with everything having the same denominator. Like all the rest of these are going to have denominators of 12. It's just going to make my life a little bit easier if I stick with that for now. We'll clean it up at the very end, but I think it's a little bit easier to just do it in one stroke here. So then we also have 5 pi over 12 plus 2 pi k over 3. And we have 7 pi over 12 plus pi k over 3. And then we just have pi over 12 plus pi k over 3. Now I can make this a little bit easier on myself, although I don't really need to, but I want to point out that like you could condense, never mind, don't do that. It's just easier to deal with it this way. Alright, so first thing I'm going to do is I'm going to get my solutions when k is 0. So I'm going to write those in ascending order just to kind of make keeping track of things a little bit easier here. Everybody's okay there? Next, I'm going to write the solutions when k is 1. When k is 1, we'd have to make a common denominator here, right? That common denominator would be 12. So I'd really be adding 8 pi over 12. Is everybody okay with that? Can we see that? Just making a common denominator. Yes? Okay. So I'm going to have, again, if I write these in ascending order, I'm going to have 9 pi over 12. I'll reduce that later. 11 pi over 12. I'll reduce that later. Nope, that one doesn't reduce. Never mind. They don't do any reducing there. 13 pi over 12 and 15 pi over 12. I'll reduce that later. Yeah, I just added 8 pi over 12 to each of those. Okay? Right, no big deal. So, these are all still less than 2 pi, right? Well, stands to reason maybe I can add 8 pi over 12 again. So if I do that, I'm going to get 7 pi over 12. And this is, again, this would be for k equals 2. I'd get 19 pi over 12. 21 pi over 12. I'll reduce that later. And then 23 pi over 12. All of those are still less than 2 pi, right? Everybody agree with that? 2 pi would be 24 pi over 12. They're all still less than that. If I add another 8 pi over 12, if I just look at the smallest one, I'd end up with 25 pi over 12, and that's too big. So I know I'm done right here. So if I really care to, I can go ahead and reduce these ones that can reduce. So like this one could be 7 pi over 4. This one could be 3 pi over 4. And this one could just be pi over 4. If you wanted to, I wouldn't get too bent out of shape about not reduced. Ben? So I'm just making a common denominator here. To add these two fractions, I need the common denominator of 12. So I multiplied that by 4 over 4 to give me like 8 pi over 12. Cool with that? So that's why it's 8 that I did over and over and again, just for the fraction purposes. And this is really what makes these problems the most kind of irritating, is having to deal with all the fraction involved in like adding and subtracting fractions. But it's not so bad, right? You're just picking values of k, and if you really need to, you can use your calculator to do the adding and subtracting of fractions, right? We all know how to do that on our calculator. Yeah, you ignore the pi's and put them back in at the end, and the calculator will handle the fraction adding for you if you need to check it or whatever. But once you find the common denominator, it's not bad. You're just doing the same adding every single time. What do you guys think on that one? Is it okay? We're going to stop here. There's still one more kind of solving problem, or like complication we can make to these solving problems that I still want to talk about next time, but I think this is enough for today. I'd like you to look at 31 to 46 from the homework set. I know it's a lot. Beware, some of those in there are ones that you'll need to factor. Remember we talked about factoring last lesson? We did an example of looking at one of these trigonometric equations as a polynomial and factoring it like a polynomial. You will have to do that in this problem set, so watch out for those ones.